Hi everyone, thank you for checking out my talk. My name is Jeff Speedie. I'm a graduate student at the University of Victoria, working with Rubing Dong in collaboration with Richard Booth. So in this work, we ask a very simple question. In the many beautiful ALMA continuum images, we see all sorts of substructure, and we think they could be gravitationally carved by planets. But we know from theory and simulations that planets drive spiral arms. This is just a well-known consequence of planet-disk interaction. So where are the planet-driven spiral arms? Well, planet-disk interaction is basically planet-gas interaction, meaning planets drive spiral arms in the gas, and the dust just evolves according to drag forces it feels from the gas. So it's not immediately obvious how planet-driven spiral arms should be manifest in the dust. In this work, we try to answer these questions by running 2D hydrodynamic simulations with Fargo 3D, then performing full radiative transfer calculations on the resulting disks, and then using those to generate synthetic ALMA observations. I want to break this talk into two sections, the first on the underlying physics and conceptual ideas, and then the second specifically about the capabilities of ALMA. So in the first half, I'll talk about something that I think is underappreciated, the role of the temperature spiral, as well as whether dust spirals do look different to gas spirals. Then in the second half, I'll outline the trends you'd need to know if you wanted to write an ALMA proposal to observe a planet-driven dust spiral, as well as discuss the possibility that spirals could be hiding in the observations we already have. So, the important physics for the observability of planet-driven dust spirals. Since the quantity observed in ALMA continuum images is thermal emission, intensity, we should care about both the spiral surface density contrast and the spiral temperature perturbation. So here I'm showing dust surface density perturbation in polar coordinates for an isothermal equation of state on the left and an adiabatic equation of state with a few select beta cooling times on the right. So looking at the surface density alone, we can see that the spiral density perturbation is strongest in isothermal disks versus adiabatic disks. So just to make this comparison clear, here's a bar chart showing the peak amplitudes and the trough amplitudes at 1.7 times the planet's orbital radius. We can see that if the gas cools effectively instantaneously, as in the isothermal case, then all the spiral energy goes into the density compression, and this yields the strongest surface density perturbation. Naively then, we might expect spirals to be most prominent in surface brightness in disks that are isothermal. However, it's important to consider what the dust temperature is doing. So in isothermal disks, there is by definition no temperature spiral perturbation. But on the other hand, in adiabatic disks, some of the spiral wave's energy can go into creating a significant temperature spiral. So in the bar chart, the longer the cooling time, the greater the spiral temperature peaks. When surface density and temperature combine, the contribution from the temperature spiral turns out to matter a lot. For beta cooling times longer than about 1 dynamical time, the temperature spiral really kicks in, and as a result, planet-driven dust spirals in those adiabatic disks are significantly brighter than in isothermal disks. This is something that is very important and not widely enough emphasized. So what I just showed you was in the optically thin limit, but this holds in full radiative transfer simulations and at almost all disk radii as well. So on the left, I'm showing the intensity perturbations, again, but this time normalized to the azimuthal average for the two equations of state that we work with most in our paper. And on the right, I'm plotting the intensity contrast of the inner and outer primary arms as a function of radius for a somewhat optically thin disk with tau at Rp of 0.1. So here are the results for tau of 0.3, 1, and an optically thick case. And as is intuitive, when the disk is optically thick, the contribution from the temperature spiral matters even more. The difference between the adiabatic and isothermal cases is even more pronounced. So this is a big takeaway to keep in mind going forward. Even though the dust surface density perturbation is largest in isothermal disks, spirals in disks with long cooling times can actually be brighter because of the contribution from the temperature spiral. So knowing that, we can ask whether dust spirals actually have a different morphology to gas spirals. Since planets drive spirals in the gas, it's not a given what the dust should look like. Accompanying the spiral gas density wave are velocity spirals, so perturbations in both the azimuthal and radial velocity components. You can imagine you're a dust particle orbiting the star at almost Keplerian velocity, and you encounter the spiral density wave. You'll feel not only a density change in the gas around you, but you'll also feel the velocity of the gas around you changing. This means that there will be a relative velocity between you and the gas, and you'll experience a drag force. This drag force and the relative velocity defines the extent to which a particle of mass m is coupled to the gas, which is quantified by the stopping time, or in dimensionless units, the Stokes number. The Stokes number is a property of the dust particle. Dust of small Stokes numbers is well coupled and responds quickly to changes in the gas. So how does dust-gas coupling play out in the case of a planet-driven spiral? So this plot shows an azimuthal slice of the density perturbation in the gas at, again, 1.7 times the planet's orbital radius. And now here's the dust. At low Stokes numbers, the dust spiral looks identical to the gas spiral. But as we increase the Stokes number, the morphology of the dust spiral starts to change. It starts to lag behind the gas and drop in amplitude. So this is another important takeaway. There are two regimes. Well-coupled dust forms spirals that are identical replications of their gas spiral counterparts at the midplane, and somewhere above a Stokes number of 10 to the minus 2, dust spirals start looking different. So here's the amplitude of the dust spiral as a function of the Stokes number, normalized to the amplitude in the gas. And here's the azimuthal offset of both the spiral peak and spiral trough. We can estimate the Stokes number that divides the well-coupled and poorly coupled regimes with a timescale argument, first described by Sturm et al. 2020, where we compare the time it takes a dust particle to cross the gas spiral wake versus the particle's intrinsic stopping time. So first we estimate the azimuthal extent of the gas spiral using, for example, the full width at half max. And then we calculate the gas spiral crossing time, taking into account the additional time because the spiral is moving in the same direction as the Keplerian flow. This crossing time, T cross, is a property of the gas spiral. We then compare it to a property of the dust stopping time. And we define the dust Stokes number for which these two timescales are equal as the critical Stokes number. Overlaying the critical Stokes number on these plots on the left, you can see that it provides a decent estimate of where things start to turn over. Dust with higher Stokes number than the critical Stokes number take longer to respond to the gas than the amount of time that the spiral drag forces act on them. And so their morphology is different. So what does this mean for ALMA observations? So for a range of gas surface densities, we can calculate the Stokes number that ALMA probes in bands 1 through 10, assuming that the observed grain size is a factor of 2 pi smaller than the wavelength that you're observing at. Overlaying the critical Stokes number on this plot, we make a very important conclusion. ALMA probes well-coupled dust with Stokes numbers less than the critical Stokes number. So we expect dust spirals observed with ALMA to be identical replications of their gas spiral parts at the midplane, barring, of course, geometric inclination effects. So to summarize this section, if the dust is well coupled, the resulting spirals follow the gas spirals exactly. If the dust is poorly coupled, meaning having a Stokes number larger than the critical Stokes number, the resulting spirals have an azimuthal offset from the gas and a lower amplitude. The Stokes numbers probed by ALMA are mostly smaller than the critical Stokes number, so except at the longest wavelengths and lowest gas surface densities, we expect dust spirals observed by ALMA to reflect the gas spiral pretty much exactly. Okay, moving on to our synthetic ALMA observations. So we explore a range of parameters, including planet properties, disk properties, and observing conditions. In terms of antenna configurations, we combine observations from both an extended configuration and a compact one. So this adds about 20% to the total observing time, but it has the added benefit of improving UV sampling and recovering emission, extended emission from the background disk, as well as resulting in a combined observation that has a lower RMS noise by about a factor of 10 versus if you just used the extended configuration alone. We also explore a wide range of sensitivities. So the greater your sensitivity, the less sensitivity, the more observing time is required. The total time breaks down into on-source time for both the extended and compact configuration, but also overheads. And unfortunately, the overheads are not a fixed cost. They actually also increase with greater sensitivity because you can only sort of do so much in one go. And so multiple execution blocks are required, leading to more overheads. So just for some context, the longest integration done on a single disk to date is just over 6 hours of on-source time, so that's not including overheads, on AS205. And all the great science that's been done on TW Hydra and HL Tau involves 5-ish hours of ALMA time. For further context, the on-source time in the D-sharp disks was really quite low. It ranged from as little as 0.2 hours to 1.2 hours, with a median of about 35 minutes. So how much ALMA time do you need to detect planet-driven spiral arms? To answer this question, we take all of our synthetic observations, and I'm showing just 12 here, and we make a residual map by azimuthally averaging in the image plane. Since our disks are face-on and we know the center, this is easy to do, and we found it actually yields better results than Frankenstein, which operates in the visibility plane. We then say that if we could trace the spiral in 5 sigma contours over an azimuthal extent greater than about 90 degrees, then we classify that as a successful spiral recovery. So this figure summarizes our results. Each box here is colored according to the minimum sensitivity required to recover the outer spiral arm in each of our models. Then inside each box, I've also put the amount of on-source time that sensitivity corresponds to. That number doesn't include overheads, so the total time required is a lot more than what's shown. But the point of this figure is to identify trends. So in what disks are dust spirals most prominent? One trend we can see is that planet-driven spirals are overall easier to detect in adiabatic disks than purely isothermal ones. The contribution from the temperature spiral makes a big difference. So here is just an example at a medium angular resolution, C5 plus C8, for a thermal mass planet, going from optically thin to optically thick from left to right. And as we saw before, the difference that the temperature spiral makes becomes even more pronounced in the optically thicker disks. The second trend we can see is that if you make a residual map, if you can make a residual map, low angular resolution isn't necessarily a disadvantage. So the C4 plus C7 configuration here doesn't actually resolve the spiral, but if you compare with higher angular resolution images, the C5 plus C8 and C6 plus C9 here, that have the same RMS noise, the larger beam actually contains more signal from the spiral within one beam and results in a higher signal-to-noise detection of the spiral. So finally, I'd like to try to answer a question I heard a theorist asking observers during the Distorted Disk conference a few months ago. So planet-driven spirals are fine structures. Is it possible that they are there amongst the gaps and rings, for example in the D-sharp disks, but hiding, either because of the gaps and rings or because we just don't have the angular resolution or the sensitivity? So I think this could come down to optical depth in 2 ways. So here I'm showing millimeter continuum emission maps of our models for 3 thermal mass planets or 1 Jupiter mass planet, again increasing optical depth from left to right. So the first aspect is an optically thin disk is overall dimmer, so any spiral signals will be fainter. But second, assuming a fixed dust to gas ratio, an optically thinner disk would have both a lower dust surface density and a lower gas surface density, meaning a fixed grain size observation would probe lower Stokes number dust, and the same planet mass would open a wider and deeper gap and a narrower and more prominent ring. Wide gaps and prominent rings help to hide planet-driven spirals because the spiral is invisible inside the gap, and because the radial width of the ring becomes the only place where the spiral can stand out. This could be relevant for the D-sharp disks. Delamonde et al. Estimated the ring optical depth in the D-sharp sample to be somewhat borderline, and the Zhang et al. Inferred planet masses are quite high. So let's take a closer look at the worst case, where we have a massive planet opening a wide gap in an optically thin disk. Here, for example, are ALMA observations of that disk with really good sensitivity, around 20 hours of observing time. With a low angular resolution configuration, there's no obvious trace of the spiral in the image. At higher angular resolution, moving to the right, you can begin to see the spiral standing out against the ring. So if you stare at a disk for a long time with a small beam, the spiral could become obvious in the image itself. But if you can make a residual map, you can actually recover the spiral with higher signal-to-noise in the lower angular resolution observation. So this goes back to what I was saying earlier about the observation with the larger beam capturing more signal from the spiral within one beam. But again, this is for really great sensitivity, and the D-sharp sample went as low as 35 microjansky per beam. So let's look at lower sensitivities. Here's 15, 20, 25, 30, and 35. So you can see the spiral signal can be totally lost. And here's just a rescaling of the color bar. One thing that still lends weight to the spiral in the lowest angular resolution observation here, though, is that there's both a spiral-shaped peak and a trough just inside it. Troughs associated with the primary arm are a signature that a spiral is driven by a planet, and so you should look for peaks and troughs in your residual maps. So in summary, if you have ALMA continuum data, try to make a residual map in the image plane, and don't just plot the positive values, plot the troughs too. Planet-driven spirals are most prominent in adiabatic disks with significant temperature spirals, and spirals in isothermal disks are very hard to detect. Under certain conditions, it's not possible to detect spirals even with a day's worth of ALMA time. Angular resolution-wise, it's not always necessary to resolve the spiral, and you can pick it up in a residual map. And planet-driven spirals could be hiding in gaps and rings, particularly in optically thin disks and in observations with low angular resolution and poor sensitivity. So thank you for listening to my talk. I look forward to hearing yours or reading your posters. Please reach out if you have any questions.